All right, we're going to do another example of an area between two curves. For example number 2, we have f of x equals x squared minus 5x minus 7. So that is a quadratic, or a parabola if you want to think of it that way. And g of x equals x minus 12. It's a linear function. Now this particular question gives us the limits. We don't have to figure out where they cross. So we're going to find it from -2, x equals -2, to x equals 5. All right, now before we find the area, however, we need to figure out where these functions cross each other, because our limits might change. We might have more than one integral to deal with. So let's go ahead and do that. We're going to set f, x squared minus 5x minus 7 equal to g equals x minus 12. Step 2, we will solve for this to figure out where they cross. So basically you will move x to the left to get negative 6x. You will add 12. Not sure why I didn't show that step here. And if you add 12 to both sides, you get plus 5. Okay, so x squared minus 6x plus 5 equals 0. You can use the x method to factor this, and you get x equals 5 and x equals 1, which is two places where they cross. Now, thing is, we're only worried about from -2 to 5, and so since one of our limits is 5, this one intersection place won't matter, just the x equals 1. All right, next we're going to determine our intervals of integration. So again, that x equals 5 was already the rightmost boundary, but the x equals 1 will now break up our integral into two separate intervals. We have one that goes from -2 to 1, so our leftmost interval up into where they first cross, and then 1 to 5, which is where they cross up until our rightmost boundary, which happens to be where they cross again, and that can happen. So since I'm saying all that, let's go ahead and take a look and see what this looks like. Okay, so here's our graph. Here's f of x, x squared minus 5x minus 7, and then here's g of x, which is x minus 12. You can see that starting at -2, f of x is the function that's above g of x. So we're going to find this area between the two. And then at x equals 1, they cross, and g of x becomes above f of x. And then we can see that they cross each other again at our rightmost boundary. So basically, we're finding this area right here, and then this big area right here. We're going to add them up. So that means we need two different definite integrals. All right, so that just gives you an idea of what each of those integrals looks like. I'm going to give you a different set of steps than I did for the last one. I normally don't do that, but instead of trying to take the absolute value, there's an alternative way. It's a little bit, I don't know, it looks a little bit better, cleaner, I would say, but it takes a little bit longer. So basically, if you didn't have this graph, how would you know which of these functions is above which on each interval? For example, from -2 to 1, how can I prove that f of x is above g of x? Well, we know that they only cross at these two places. So if I plug in a test value here between -2 and 1, whatever I get back for each of these will tell me which one of these is bigger. So I can plug in 0 between -2 and 1. I get -7 for f, and I get -12 for g. That means that f is bigger than g on that interval. Okay, and if I plug in a test value between 1 and 5, say 2, I see that g of x equals -10. G of 2 is bigger than f of 2, which is -13. So that tells me for my first interval, f of x is the upper function, g of x is the lower, and then it switches from 1 to 5. If you do it this way, you don't need to worry about taking the absolute value, because you are subtracting the bigger minus the smaller for each, and the area will take care of itself. You'll never get a negative area back. Okay, so again, this is a different set of steps than what we learned before, but I think it's important so that you understand conceptually what's going on here. All right, so from -2 to 1, I'm going to do f minus g, and I will end up with a different formula than when I do g minus f for my second interval. So this one's g minus f. So that's step 6, setting up your integrals. For this method, you can do the upper minus the lower, and you will not have to worry about absolute value. Step 7, simplify each integral. So the first one, I will subtract the x and the -12. Now we'll get, this will be minus negative 12, so it'll be plus 12. So I'm going to end up with plus 5 on the right. Would it be x squared minus 6x plus 5? For the second one, you can obviously understand that it's going to be the same formula but negative, so it'd be negative x squared plus 6x minus 5. And then we were just going to find the definite integral of each of those. So step 8, determine the definite integral using antiderivatives or the reverse power rule. So for the first one, we'll have 1/3 x cubed minus 6x squared over 2 plus 5x. And I'm going to plug in my upper and lower limits. So I'm going to plug in 1, and then I'm going to subtract my lower limit when I plug in negative 2, making sure to put brackets around the second part so that I can distribute my negative properly. If I simplify all that out, I get 27. Okay, 27, which is very big. But if we go back and look at our graph, there is actually a huge area here from negative 2 to 1 between these two graphs. All right, for my second one, I want to check that real quick to make sure that 27 is right, because I don't. Let me just check that real quick. Okay, so I did confirm that it actually was 27. I guess when you zoom out of this graph, you can see that there's actually a lot of space there. Okay, so that entire area is indeed 27 between F and G. And again, this time it's going to definitely be positive because I'm doing the upper minus the lower. All right, so now let's find this second area right here on the right by doing G minus F from 1 to 5. So here is our antiderivative, basically the same thing as before, but again, everything's going to change sign. And I'm going to plug in my upper and lower limits, making sure to put brackets and negatives where necessary. And for that second area, I get 32/3. And so here's our second area, 32/3 or 10.6 repeating. Now obviously we want to find the total area between these two graphs, so it makes sense that we would add these two together. So for step 9, add up those integrals, and you get 37 2/3, which is 37.6 repeating. And again, that's what happens when you add up those two areas. And we didn't have to, do any kind of absolute value, because for this method, we determined what our upper and lower functions were for each interval, and that takes care of itself. So it's a different method, but I think it's important to conceptually understand the difference between upper and lower graphs, and it works equally as well. So that's it for this particular example. If you have any other questions about this, let me know.